Hey, good morning, SE301. Hey, before we start today's lesson, Lesson 10 on alternative generation, I have a quick announcement to make about the course project. My department leadership wanted me to make sure that all of you are tracking that the results of your project are not part of any sort of academy initiative, nor will the results of or the solutions that you all develop actually be implemented by the academy or shared with anyone at the academy leadership. The academy is using the military decision-making process and going through the standard mission analysis type processes to come up with their courses of action. And the main purpose of the project is to let y'all use your systems engineering problem that you are somewhat familiar with and that's interesting and relevant. But again, I think most of y'all were tracking that it's not part of any sort of actual academy study. But I wanted to make sure that that was very clear. All right, so getting into today's lesson about alternative generation, um, we're currently in the solution design phase of the course. We learned in the last lesson about design methods, about ideation, about different solution design techniques. But what we're going to look at is alternative generation. And alternative generation is important because when you start looking at systems, there's a lot of components that go into that. And so you might have a lot of different permutations, and it's useful to have a large number of different alternatives that you can use to try to evaluate as possible solutions to whatever problem you're trying to solve. And once you have a large number of alternatives, we'll also look at how to screen them down and do some feasibility screening. So today's lesson, we're going to look at alternative generation approaches. Zwicky's morphological matrix, which is kind of the core way that we do alternative generation for this class. I'll show you two examples. One's a slightly fun example, and one's an actual TALOS tactical assault light operator suit example from a project that I've been working on. And then, so alternative generation is fairly straightforward. You can see it. You can see right here this nice little diagram. Up here at the very top, you have your ideas, and this comes from generation, which we talked about last lesson. So when you do idea generation, you brainstorm, brainwriting, affinity diagramming, all those great things, you have a lot of ideas. So the first thing that you do is you put that through a needs filter, and you look at, okay, which of these ideas will actually meet my stakeholder needs? And so that takes out a number of solutions and gives you just a number of feasible solutions that you can look at. And a lot of times that filter is enough. Like, hey, you have your feasible solutions, let's roll with that. Other times you'll apply another two levels of filters to look at wants and desires, and you'll get down to the very bottom where you only have a handful of your ideas that come down as solutions. And so that's a common way to try to filter down from all your ideas to a handful of enhanced solutions. But when we talk about ideas and everything, and we look at our different alternatives, when we focus on ideas, we're focusing on individual components typically of our So when we're brainstorming, say for your course project, when you're brainstorming academic policies that could be implemented by the academy, you could have all classes go virtual, classes go hybrid, classes stay in person, classes get smaller but practice social distancing. There's classes move outdoors. There's just a lot of ideas that are out there. But that's only looking at one component. Now, when you start looking at military training, there's a number of different ideas that come out of that as well. And when you start piecing these all together, it gets very complex very quickly. So a common technique that we use to actually generate your alternatives is Zwicky's morphological box. So it explores combinations of components through the study of form and structure. And what you have to do with Zwicky's morphological box is basically you create a box, or matrix, if you will, where in each column you lay out your different design parameter that you can care about, or your different component that you care about. And you list out all the different possible ideas that are feasible. And then you look at different permutations. And as you go across from column to column, you just pick one item from each column and you come up with a alternative. You come up with a solution alternative or a design alternative. And it's a good way to keep everything organized and try to look at different alternatives. Normally what you try to do when you use Wiki's morphological box is you create a strategy. So you look at all your different alternatives, and when you're picking things from different columns, you keep something in mind. Say you want the lightest option out there. Every column you pick the lightest component. Suppose you want the cheapest option. Every column you pick the cheapest component. Suppose for your course projects you're looking at West Point's response and you want the least disturbance to the norm. Every column you would pick something that's close to the status quo. So while this chart right here, this PowerPoint slide has a lot of words on it, it's more useful to actually look through some examples. So right here we can look at a lamp solution design, and you have Zwicky's morphological box. So you have 7 columns here. Each column represents a component of that lamp. So you have your power supply, your bulb type, your light intensity, size, style, finish, material. So suppose you wanted to go for a kind of a standard IKEA style lamp design. You could have a power supply being battery, bulb types being just daylight bulbs, a variable light intensity. You have a large lamp, not a very large lamp, just a large lamp, industrial, with a metallic finish and made out of metal. There are certain things on here that wouldn't make sense. So you would probably not go for an industrial look with a terracotta finish. So when you go from column to column, you have to keep some level of consistency. Another alternative would be if you wanted some sort of old school 1800 style lamp, which is powered by gas. You have a standard bulb, low light intensity. It's fairly small because it's, again, supposed to be representative of the 1800s. A modern style, which actually modern lamps actually reflect older looking lamps as well. The black finish, and you're making it out of glass. So that's a option as well. So again, you're just picking one thing from each column as you go along, you piece it together, and that creates your design alternative. So working through another problem, and in the past this has been a board problem that we've done, where we've had folks create burger designs. So you build Zwicky's morphological box. The first thing you have to do is you have to identify what columns you want to have. And so give them some recommendations, like you can have your meat, you can have your bun type, you can have cheese, vegetable, special toppings, sauce, and you can develop burger strategies with that. So if I were to create a morphological box for a hamburger, you can see right here that I have 6 columns: meat, bun, cheese, vegetable, special topping, and sauce. Now, my first strategy I want to go with is I want to go Pittsburgh inspired. My wife's from Pittsburgh, so I let her pick out what she thought would be most representative of the Pittsburgh culture. So she went for a turkey burger because Pittsburgh's evidently gone young and hip, and folks are kind of going into alternative meats for burgers. A white bun, Swiss cheese, coleslaw as a vegetable, French fries as a special topping, and Dijon mustard. And it's supposed to be representative of a Permani sandwich, if any of y'all are familiar with Pittsburgh. Strategy 2, Texas inspired, being a proud Texan myself. Go with beef, a white bun, cheddar, the only type of cheese out there really. Lettuce, because who wants tomato, and coleslaw is just gross. Who needs a special topping when you have good meat? And ranch, because ranch goes on everything. Then suppose you wanted to do a Boston inspired burger. You'd probably go for like a lean beef, whole wheat, gorgonzola, because they're kind of fancy up there in the Northeast. Lettuce and tomato, because onion rings, because why not? It's Boston. Then mustard for good measure. This is kind of a notional and kind of a fun example just to walk you through Zwicky's morphological box and coming up with a couple of burger design alternatives. But what I want to talk about now is an actual Zwicky's morphological box that was used in the real world. So again, my sections heard me talk a lot about TALOS. I mentioned it a little bit in Lesson 9, but Special Operations Command tried to build an Iron Man suit between 2014 and 2000. The project got canceled last year, 2020. And the basic premise was that they wanted to protect the first operator through the door on hostage rescue missions. Um, and when we started doing the functional decomposition of TALOS and looking at all the different components that went into it, we found that it had these following 6 components. It had exoskeleton, had armor, had power, had situational awareness, um, like capabilities, and communication devices, and weapons. So you can see that each of those is represented in a column in this morphological box. For the exoskeleton, we had 3 different alternatives: electric, pneumatic, and hydraulic. We had armor coverage. We had full armor coverage, 70% and 50%. So that kind of decreased your mobility even with a fully functioning exoskeleton. So we started evaluating what happens if you give less armor coverage. Then you have your power system. We looked at batteries, fuel cells, and we looked at small 2-stroke engines that with a hybrid battery option. Situational awareness, we looked at look-down displays. So imagine what the Google glasses were, but actually with a much nicer interface. With you wear glasses and you have a couple of screens that you can look down at built into those glasses. Augmented reality, similar to the Microsoft HoloLens, you can just look through them, and data is superimposed onto that screen that you're looking through. Communication, we only had one option. We're going with a digital radio. Then the weapons, we're looking at a standard M4 as well as an upgraded weapon that integrated in with your situational awareness. So we developed 2 strategies. The first was what's called TALOS Lite, and this was intended to kind of give us one end of the design spectrum where we're trying to figure out, hey, we move to the objectives, moving through the objective, be quick, so we don't want to weigh down someone with armor. So we went with the lightest weight option, so an electric exoskeleton, 50% armor coverage, a battery, look-down displays, digital radio, and M4. And the goal was to keep it simple, because as you add complexity, you add weight, and so the operator would be the least encumbered with this. We're going to basically put the guy inside a heavily armed skeleton, and imagine like a mech suit or something where the guy is crushing through the objective. So in that case, we're looking at a pneumatic exoskeleton with full armor coverage. We're using a 2-stroke engine because we needed that power to power everything and support all that armor. It's all a very complex design that went into that. Augmented reality, a digital radio, and then upgraded weapon. So that's the TALOS heavy option. And keep in mind, these were actual design alternatives that we not only conceptualized, but we also got build tested, all went through user evaluations. So one question would come up if, when you're looking at this morphological box, how many different design alternatives can you have? You can have 3 exoskeletons, 3 armor coverage, 3 power systems, 2 situational awareness, 1 commo, 2 weapons. So that would lead all together, if you look at every single permutation, you would have 3 times 3, so 9 times 3, 27, times 2, 54, times 1, 54, times 2, 108. So you would have 108 different possible design alternatives that are possible. But would it make sense to have an electro exoskeleton with full armor coverage with batteries? It wouldn't. The reason is pretty straightforward. An electro exoskeleton wouldn't be able to support full armor coverage. And even if it could, if you used a battery power system with full armor coverage, you'd only get like a half an hour of useful time in the suit. So you can see that there's certain alternatives that just get rolled out, that can get rolled out. And that's what we do in the next step, which is called feasibility screening. So feasibility screening is where we take the different alternatives that we generate through Zwicky's morphological box, and we put it through a filter. We look at needs. And if we still have a lot of alternatives, we look at wants. If we still have a lot of alternatives, we look at desires. And if we, and at that point, we should be at a good place to have a good amount of design alternatives, but not too many that we burn ourselves with the following steps in the process. So when you look at screening criteria comes from the stakeholder requirements. So all the way back to problem definition, and the reason we do problem definition is to understand what the stakeholder needs, wants, and desires are. Needs, they must have this. TALOS must protect an operator's neck. Wants, TALOS should enhance their mobility. Desires, nice to have. We'd love for TALOS to fly. So needs, wants, and desires. Solution designers may choose to initially screen at only the needs level or may add screens from wants and desires. And that's what we were showing you on that last figure. As you go further down, it just adds another level of screening and limit yourself on your number of alternatives. All right, so this is an example taken from page 368 of the book, looking at different rocket alternatives, but this is what's called a feasibility screening matrix. So each row in a feasibility screening matrix is given for a design alternative that comes out of Zwicky's morphological box. And here we can see that there are three criteria that we're using for feasibility screening. So your stakeholder is saying that the range of this rocket has to be greater than 500 kilometers, has to have a mobility criterion greater than medium, and a terrain criterion greater than all. Don't worry exactly about what that means. Parameters that you're screening for. So if you have a range value for any of your alternatives that's less than 500 kilometers, you rule it out. It's not feasible. If you have a mobility criterion that is medium or low, it's not feasible also. If you have a terrain criterion that is not all, it's not feasible. And if anything, and if your design alternatives, if they don't meet any one of these three criteria, it's considered overall a no-go. So right here we can see for global lightning, it has a range criterion of 800 kilometers, a mobility criterion of high, and terrain criterion of all. So it gets an overall go. But when we move here to alternative sight and sound, you have a range criterion of 700 kilometers, so that's good, you get a go. Mobility criterion of high, so you get a go there. But you have a terrain criterion of limited, so it's a no-go. So overall, this alternative, sight and sound, is a no-go. Similarly, with the 5-fin alternative, the range criterion is 400, so you get a no-go there. But you also get a no-go over here because you have limited terrain criterion, so you get a no-go overall. So the main purpose of doing you want to make sure that you don't overwhelm your systems engineers while you're doing the next steps in your process, and that you're not considering designs that won't meet your stakeholder needs, because that's just a waste of time. Last thing that you ever want to do is get to that last step, have a solution design, take to your stakeholder, and they say, hey, this doesn't meet one of my base criteria. Yeah, that's a bad day. So it's important that when you do your feasibility screening, that you make sure you do that. All right, so in today's lesson, we talked about Zwicky's morphological box and feasibility screening matrix, and all of this should feed directly into your course project. And remember, for WPR2 and for the T, you will be expected to not only, or you'll be expected to, given Zwicky's morphological box, look at how many different design parameters you have, develop strategies, develop design alternatives, and then do some sort of feasibility screening with that. All right. Well, that wraps up this lesson. We only had one block of it today. I hope you all enjoyed it and have a great rest of your day.